We're also going to categorize our equilibria types by the shapes of the solution curves. We'll start out with spirals. And the reason for the name spiral is pretty obvious. If you look at these two in example 5, they clearly have a spiral shape that's either leading toward the origin or away from the origin. One way I like to think about the phase plane is I think of looking like I'm looking down at the surface of some water, and the water has currents in it. And all the little solution curves are currents. So, for example, if I were to drop a rubber ball, say here on the surface of the water, it's going to travel this way because this current is pulling it that way. Or if I drop a ping pong ball, say there, it's going to travel this way along that current. These two phase planes in example 5 go along with the differential equations that I've put up here. I got them from Wolfram Alpha, and let me just remind you that this matrix notation is a shorthand for saying dx1 dt equals negative x1 plus x2, and dx2 dt equals negative x1 minus x2. So over at Wolfram Alpha, I entered minus x plus y for the first equation and minus x minus y for the second equation. Similarly, for this other one, the matrix equation is shorthand for the system of differential equations dx1 dt equals x1 minus x2 and dx2 dt equals x1 plus x2. So over at Wolfram Alpha, I entered x minus y for the first equation and x plus y for the second equation. And I went in detail over how to do that in an earlier video. So if you don't remember, you can go back and watch that. I also got rid of the XY axes labels. Well, I also put in axes, and again, I showed you how to do that in an earlier video. And I got rid of the labels X and Y for the axes that Wolfram Alpha puts in because we need to call our axes X1 and X2. I'm just going to label those by hand. And similarly for this one. Now you can see in the first one that all of the currents or solution curves are spiraling in towards the origin, towards that equilibrium point. So this one is a stable equilibrium at 0, 0. If you look at the second of these two phase planes, notice that, yeah, it's a spiral, but all the currents are going away from the origin. So it's still an equilibrium point, but it's an unstable equilibrium at 0, 0. So if my rubber ball is right on the origin, yeah, there's going to be an instant in time when it's not moving in either direction, but then right after that first instant in time, one of the currents is going to start pulling it away from the origin. Whereas over on the stable one, even if I don't drop my ball right on the origin, it's going to get pulled towards the origin by the currents. And even if something pushes it off that equilibrium point a little bit, the currents are going to tend to push it back to the equilibrium point. So it's going to be stable or fairly stable at the origin. Another type of equilibrium point is called a saddle. And an equilibrium point is a saddle if the motion in the phase plane is toward the equilibrium along some solution curves and away from the equilibrium along other solution curves. Notice that automatically means that these have to be unstable, because remember, an unstable equilibrium has some of the curves leading away from the equilibrium point. And here's an example of one. Dx dt equals 0, 1, 2, negative 1x. Again, that's another way of representing the system of differential equations. Dx1 dt equals x2, and dx2 dt equals 2x1 minus x2. And again, I got that from Wolfram alpha. For the first equation, box over at Wolfram alpha, I entered just a y. And for the second equation, box over at Wolfram alpha, I entered 2x minus y. Again, this is just what you're going to enter at Wolfram alpha, and I showed you how to find that in an earlier video in this series. So we already said this was an unstable, because it's a saddle, unstable equilibrium at 0, 0. But let's look closer. Let's look at these solution curves and see if we can spot that they are, some of them going towards the origin and some are going away. So like this one, for example, the arrows are pointing toward the origin, whereas go along this way, you're going away from the origin. So if I drop my rubber ball here, the current would take it toward the origin, but if I drop my rubber ball here, the current will take it away from the origin. If I were to drop my rubber ball right on the origin, what's going to happen? Well, if it drifts off into one of the currents that pushes it back towards the origin, yeah, it'll go back towards the origin. But if it drifts off and hits one of the currents that takes it away, it's going to shoot away from the origin. So that is not a stable situation. We cannot count on the rubber ball remaining stably at that equilibrium point. There will be an instant in time when it's not moving in either direction at all, but that may not last. Now, I wanted to just mention why this type of situation is called a saddle. And it's named after the saddle that you'd put on a horse. And there's another object in the real world that also is called a saddle and gets its name from the saddle you put on a horse, and that is this type of configuration with hills or mountains is called a saddle. And right in the middle of the saddle here, we have an equilibrium point. I'm thinking of gravity now instead of water currents. But if I put a ball right there, what is it going to stay there? It'll balance there for at least a moment in time. But suppose, a breeze moves it a little bit. What's going to happen? Well, it depends. If it gets moved up the side of the mountain, then it's just going to come back down. So those directions will tend to push it toward the equilibrium point. But notice if it goes off the equilibrium point a little bit, going this way, going downhill, it's just going to keep going downhill. So that is not a stable point of motionlessness. It's unstable. The ball might stay there, but depending on what happens, it might get started rolling downhill and never come back to the equilibrium point. So you can't count on it staying there. And that's the kind of situation that in this context is also called a saddle, where you've got some directions where you'll roll back or get pushed back towards the equilibrium point, but some directions where you'll roll away or get pushed away from the equilibrium point.